Okay, so let's get into chapter 2 stuff. There's something called, position, displacement, distance, path length. What's used in this book is position, which describes an object's location with respect to a particular coordinate system. So when you're doing a problem, you always have to kind of set up a coordinate system, put your X and Y somewhere, try to specify where your origin is so you can specify what your position means, because it's going to be a number. Displacement is your change in position. So we usually do the final minus the initial. And then the magnitude of the displacement, since displacement is a vector, you can have how far that vector is. And then there's another thing, sometimes called path length, also called distance traveled, which is how far an object may have moved during that time, from whatever initial time to final time. So path length, imagine laying a string along the path that the object took. The length of the string is the distance traveled. We'll try to do some examples of that today. Let's start with, let's actually draw something out. Let's talk about an example where a car backs up, moving in the negative direction, towards the origin of the coordinate systems at x equals 0. The car stops and then moves in the positive direction to its final position. So the car actually starts here at x, 0. And then it's going to, that's a car, by the way. So this is the initial position. Sometimes it's the position at time 0 or something, so you put x sub 0, the subscript 0. And then when you put x sub f, that stands for final position. And so the car ends up here. What's interesting is that it goes backwards to the origin and then turns around and comes back here. But really, to draw a position, there's just two. This is car like initially and then final position. So next slide is displacement. So the displacement, I guess you can just kind of get from that diagram. I think I'm going to put it on this previous diagram, is that you've got delta x. I've got to draw my delta a little bit better. So delta is a triangle. It's a Greek letter. X, this is delta. Means change in. The change in x is equal to x final minus x initial. And so it includes a direction. This is called displacement. So we're going to learn about vectors. Displacement is a vector. It has direction. But the magnitude of the displacement, this book just puts little absolute value signs around it, is going to be, in this case, just x final minus x initial. It's going to be some number. And this we call magnitude of the displacement. So it's just sort of defining things here. And then there's the distance traveled. In that case, you have to actually consider what happened with the car, which is that it backed up. It went this way, and then it turned around and came back all of this way. So it went this distance, I guess, if this is x initial, it kind of went that whole x initial back to 0, and then it went this whole x final distance there. So the distance traveled, I would say, is x initial plus x final in this case. Right, because first it went back, and then it did the whole distance from 0 back to 0, then 0 to xf. Which is funny because x delta x was the difference, right? Magnitude of the displacement was x final minus x initial. And so that's going to be less than x final plus x initial. So less than d. And generally, I think that d is greater than or equal to delta x. So next thing I want to do is get to time, and then we're going to try to measure a speed. And I've got a volunteer helping me with a particular measurement, but we'll get there in a minute. So what is time? Well, time, I guess, in physics is just whatever you read on a stopwatch. And Jonathan, do I have a stopwatch somewhere? Oh, on the table. Okay, thank you. We're going to make so a time interval, t, maybe t final minus t initial, or t2 minus t1, is a difference in time readings. So you put a delta, that triangle on the t, and you get delta t. And it's a scalar quantity, so unlike position or displacement, it doesn't really have any direction associated with it. It's just a number. And the SI unit for time is seconds, which is what we'll use today. Average velocity is the displacement divided by the time interval. So if an object is moving steadily with constant velocity, then the velocity is actually the rise over run of a position versus time graph. So if you were to make a plot of time on the horizontal axis and displacement on the vertical axis, and you had a graph there, then the delta x would be your rise and the delta t would be your run. So we're going to go through some more of this stuff, but the speed and direction together are called the velocity of an object. So what I want to try to do is the wave, and what I need is for a lot of audience participation for this one. We're going to try to measure the speed of the wave. So it's going to start with people over here on the right-hand side of the room, and then the idea is that you have to stand up, say, whoa, and then sit back down. But you don't do it till the person beside you stands up and goes, whoa, and sits down. So you just wait. Everyone wait until the person beside you stands up and says, whoa, and sits down. And what should happen, if we start with you people, so everyone on the right-hand side of the room will stand up and say, whoa, and sit down. If you're just sort of here, if you don't have any neighbors to your right, basically, then you start the wave. But the rest of you just wait till your neighbors stand up to say, whoa, and then you join in the wave. Does that sound good? And what we're going to try to do here is, I think as I mentioned here, I counted 70 seats around the circle. So we're going to do this in seats, and then we're going to convert to SI units. So what I need, I'm going to get this, actually. Did you measure the distance? But can you tell me what the distance is between seats?
It's 51.2 centimeters.
How much?
51.2 centimeters.
So 0.512 meters is one seat. Okay, so that's going to be our conversion factor when we, I think we'll measure delta x will be 70 seats. That'll be our unit of distance. Thanks so much, I appreciate it. What's your name? Austin, thank you very much. Okay, very cool. All right, so are we ready? I need the stopwatch. So I'm going to measure how much time to go through all 70 seats kind of around to there. And anyone can participate. I don't know how it's going to propagate over the floor, but be ready. So again, if you don't have any neighbors just to the right of you, you're going to start on the count of 3. Ready? 1, 2, 3, go! All right, nice. 12.56 seconds. Very, very good. Well done, everybody. So I got delta t is 12.56 seconds. So the speed is delta x divided by delta t is 70 divided by 12.56 seats per second. And then we can convert that, actually, multiplying by 0.512 to convert to meters per second. So times, it's good to convert these things to SI units. 2.85. So that is V is equal to, it's going to be 5.57 times 0.512 divided by 1. So that'll convert meters, and this is meters per second. And what's interesting is you can actually compare this to the literature, human waves in stadiums. So this was a paper published in 2003 by some Hungarians, actually, who were watching videos. And what's interesting is they got 22 plus or minus 3 seeds per second. So, and whereas we got 5. So I think, maybe there's something about being in a Mexican sports stadium and you're all hyped up and eager, and you see the wave coming from a long way away, that really speeds up the wave. So I think it has something to do with how much energy people have. This is Monday morning. That's another thing. If we did this Friday afternoon, we might have a higher speed. So, okay. So that's our speed calculation. Thank you for that. So this is a position versus time graph. Position goes traditionally on the vertical axis, and then time goes on the horizontal axis. So it's a little bit strange. The slopes here are going to be, rise over run is in meters per second. So, example, imagine you steadily walk 7 meters away from your house in 5 seconds. So there's position 7 meters, there's walking, and you're going at a steady speed, so it's a steady slope. 5 seconds later, time in seconds, there you are. Then you stop and you look around in your bag and realize that you forgot your phone, so you run back to where you started, and it only takes you 3 seconds to get back to where you were. So that's your position time graph. And what's interesting about this is that you can see your speed is proportional to your slope somehow. So if you go a farther distance in a shorter amount of time, that's a steeper slope, so that's going faster. If you go a shorter distance and it takes a longer time, or it takes a longer time, then that is a slower motion. And if time is going by on this horizontal axis, but your position isn't changing, then that means you are stopped, you're not moving, or you're at rest. I've seen this asked on a end of chapter or a test problem. It says, you hike 2/3 of the way to the top of a hill at speed v1, and then you run the final third at a speed v2. What was your average speed? And you can't just add up the 2 speeds and divide by 2. That's not going to work. So the first thing you should usually do is draw a diagram. So here's a guy, and here's a hill. He starts off with v1, and then goes, so I think it says that 2/3 of the way. This implies distance, not time, and that's important. Of the way, I think, is what, to me, means that this D1 is something like 2/3 of D, where D is this total distance here that he travels. And then for this last bit, he's going V2 up to the end. This is D2 equals D over 3, something like that. So what we need, I guess, V average is going to be D divided by the time. So what we need is the total time. Because we have D, T1 is the time for the first, I would say 2D over 3. And T2 is the time for the last, D over 3. And this is the definition of average velocity. The total distance divided by the total time. So time is equal to T1 plus T2. You know that V1 is the distance that it travels in T1. So that would be 2d over 3 divided by t1. So I think you can solve that out. You can say that t1 is equal to 2d divided by 3v1. And you also know that v2 is equal to d over 3 divided by t2. And that means that t2 is equal to d divided by 3v2. So the v average from this equation here is going to be d divided by t1 plus t2. So it's d divided by 2d over 3v1 plus d over 3v2. So now that you have to do some algebra to try to simplify that out, I guess, or you should do. Although I guess that's the answer. What I could do is times the top and bottom by something that simplifies this a bit. So get rid of the 3's on the bottom, get rid of the d's on the top. Multiply top and bottom by 3 over d. So you get v average is equal to 3 divided by 2 over v1 plus 1 over v2. Still doesn't look very simple, but I could multiply top and bottom to get rid of those fractions in the bottom, by v1 times v2. v1, v2. So I get 3 v1, v2 divided by 2 v2, I guess, plus v1. So it's definitely not just adding the two speeds and dividing by 2. Yeah, so if you have a position versus time graph, you can get what the slope of that is. So you would say, but that's not always constant. So here it looks like the slope is increasing, maybe up to here. And then it decreases, maybe down to about here. And then it increases again. So what I would say is that at every point, there's like a tangent, delta x divided by delta t. V is equal to delta x over delta t. Those are deltas. And then you could also do little tangents here, where the delta v and delta t, you would say that the acceleration is equal to delta v divided by delta t. So the same process of taking slopes at a bunch of different points and then plotting those slopes, you can do that for the velocity versus time graph. And now the slope is called acceleration. And so what you could do here, for example, if you have a parabola, x versus t, then I would say v sub x is the slope of x versus t graph. And some people call this the derivative in calculus. And then the a sub x is the slope of the v versus t graph. Again, it's the derivative. So the time derivative of position is velocity, and the time derivative of velocity is acceleration. You can also go backwards down. So there's something called the area under. This is what I was going to talk about. We'll talk about it more on either a Friday or a Monday, which is that v sub x is the area under the graph of a versus t. So you can kind of find the area here. It's a graphical method called an integral. So this is when, in calculus, some people say that derivatives, and like integration is the opposite of differentiation. So that's what this means here, is that x is the area under a graph of v sub x versus t. Okay, this is again an integral. So we'll talk more about those graphical methods in a bit. I also asked you at the end of class last time to think about, does constant velocity imply constant acceleration? And the answer there is, yeah, it definitely does. In fact, it implies that the acceleration is 0, which is a constant. Okay. What about the other way around? Does constant velocity imply, does constant acceleration imply constant velocity? In that case, the answer is no, unless I guess that constant happens to be 0. What a constant acceleration situation is it means that the velocity is changing at a constant rate. That's kind of what you should think of. The acceleration is just giving you a feeling for how fast something is, or how much it's speeding up by, like how many meters per second does it gain every second. So also, velocity is a vector. It has direction. And in one dimension, we specify that direction by giving it a sign, usually. Acceleration is also a vector. Let's try to review this and go over it a little bit better. And in fact, this was, so many students were asking, this is just 3 of them from this morning, but there was, I don't know, there must have been 20 questions, all asking for the same sort of thing. What the heck is deceleration, and how is that different from negative acceleration? So let me go over that. So I think in common parlance, to accelerate and to decelerate are opposites. But what's interesting in physics is that we don't do it that way. We say that deceleration is kind of like a subset of acceleration. So in fact, I don't even use the word deceleration. It doesn't really help anybody. I just say accelerate. So in physics, the word acceleration is more general, okay? And deceleration is like a special case of acceleration. But so better to just use acceleration. That's the important concept here. If an object's velocity is changing in any way, because it's speeding up maybe, it's slowing down, or it's turning, whatever, then it has acceleration, and this acceleration can be measured in meters per second squared. You don't need to even use the word deceleration. So, but if you want to, I think deceleration means that's slowing down. But, okay, so that's the word deceleration. Let's just avoid it. If you don't like it, don't even use it. Just use acceleration. So, next step, the sign of acceleration. This is kind of hard, but if you listen carefully, you'll kind of get it. So, and we'll do a demo pretty soon, but it is. Okay, first step is, if you're doing a problem, draw a diagram. Draw a diagram, draw a diagram. So, when you draw a diagram, you should label your axes. You should define a coordinate system somehow. You can put your X and Y or whatever. And when you do that, you put little arrows on it, you are defining what the positive direction is. So then, if something's moving in the plus X direction, you say its velocity is positive. If it's moving in the opposite direction, say the velocity is negative. Makes sense? Then, this is the tricky part. If something's moving in a straight line and it's speeding up, then I say that the sign of the acceleration is the same as the sign of the velocity. So if you're speeding up in the positive direction like that car was, then the velocity is positive and the acceleration is also positive. But I guess if you're going in the negative direction and your velocity is negative and you're speeding up, then your acceleration is also negative. And then if something's moving in a straight line and it's slowing down, that means that the acceleration vector is opposite your velocity vector. It's killing your velocity, right? So, and that's exactly what you guys figured out when the car was slowing down. Its velocity was positive, so its acceleration, or to the right, so the acceleration must have been to the left. So if you specify, if you've drawn an axis, and you're specifying direction with a sign, then the opposite direction means an opposite sign. Let's do this demo here, but first, so think of an object that, an example when an object, are you ready to do the video maybe? Example where an object with negative acceleration, which is speeding up, positive acceleration, which is slowing down, or an object with zero velocity, which is accelerating. So I'm going to try to demonstrate all 3 of these things with this track. And I'm going to say, let's define plus x to be to the right. So let's maybe hit the video. Yeah, there we go. So to the right is that way, right? Yep. Okay, good. So plus. That's now, so my first step is to define which direction I define to be plus. So I was going to say, think of an example with negative acceleration, which is speeding up. So if I turn this on, there you go. It's already set up that way. So now I've got something, since plus is to the right, then the v sub x, meaning the velocity component in the x direction, is negative if it's moving to the left. So that's the first thing. Also, since there's a fan on, which is getting it to go faster and faster and faster, the acceleration is in the same direction as the velocity. So the acceleration has the same sign as the velocity because we're specifying direction by sign. So negative velocity means negative acceleration. So this is something negative acceleration and speeding up. Think of an example of an object with a positive acceleration, which is slowing down. So it's positive acceleration, and its acceleration is opposite the velocity. So I need negative velocity. Yeah, so what I'm going to do is this. And then I'm going to throw it. Okay, so what was going on there, it's kind of hard to see, but I started it with a fast velocity and it slowed down, slowed down, slowed down. So what's going on there? It has a negative velocity because it's moving to the left, and since it's slowing down, the acceleration vector is opposite the velocity vector, so it's a positive acceleration. So this is something of positive acceleration and it's slowing down. Let's see one more time. And I think, the acceleration is the way that the force is pushing it, right? The fan is pushing it to the right. So it's got a positive force, a positive acceleration. Third thing, think of an example of an object with zero velocity, which is accelerating. How can you, yeah, I know, now I remember. So what we can do is watch it until it stops. Whoop. Now it's going, so. It turned around. So what I think is that the velocity started off negative, and then it became positive. So if you smoothly go from a negative number to a positive number, I think you have to pass through zero, right? So what that means is at this point where it was turning, the velocity was zero. But is the acceleration? No, the acceleration is always going to be positive for the whole case because the fan's on, it's blowing it so it's going to be positive acceleration as it's slowing down, positive acceleration as it's speeding up. Does that make sense? Yeah, because now it's speeding up and the velocity actually has switched to be positive. So you've got acceleration and velocity in the same direction, so it's speeding up. So the acceleration doesn't change in that case. You got a question back there? Are you a good catcher? Ready?
Okay. I have a question. When you initially push it in the very beginning, what's the acceleration, positive or negative?
Oh yeah, the push. That's a really good question. So during the push, I must have had a negative acceleration, yeah, because it's in this direction. But as soon as I let it go, and the fan's the only thing, then suddenly the acceleration changes to be positive. Really, really good point.
Do you want it back?
Yeah, sure. All right, good. This thing is so tough. Luckily. So I haven't tried throwing it up to the balcony yet because I haven't seen it. I don't think I could do it, but maybe I could. Okay. All right, I think we're doing great. So, someone asked this great question as well. Another good question from the survey. Is there a rate of change of acceleration? It's sort of the obvious thing, right? We took a rate of change of position and got velocity. You could take a rate of change of velocity, get acceleration. What about rate of change of acceleration? So yeah, you could take the slope of the acceleration versus time graph and get jerk in meters per second cubed, but no one ever does that. And I say because it's not very interesting, doesn't relate to anything. So why did we get to acceleration anyways? Because, this is the secret, and we're going to get into this in chapter 4, is that acceleration is extremely useful in physics for solving problems and figuring stuff out. Because it is directly proportional to the net force in an object, and it's inversely proportional to the mass of an object. And so that's Newton's second law. Acceleration comes up. And so it seems like a crazy way to start an algebra-based physics course is to introduce the second time derivative of something, a position, but we kind of have to. We're forced to do it because acceleration is just so crucial for our understanding of Newton's laws and how things move. So there's some equations. Where are we here? Yeah, we're doing great for time. They're derived in the textbook, so I think I'm not going to go through the derivation. I'm just going to show them. There's equation 2.52, which says that so actually, by v, I think what it means is the final velocity. V equals final velocity. And v0 means initial velocity, so they don't put a little f on the v. Equals the initial velocity plus the acceleration multiplied by the time. Then there's equation 2.53, which is this 1/2 at squared thing. If you're trying to find how far something goes, it's the initial position plus v0 initial velocity times t plus 1/2 times a times t squared. Equation 2.54 looks like that. You've got the final velocity squared is the initial velocity squared plus 2 times a times x minus x0. And what I do if I'm solving a problem is that first I draw a diagram, then I list my kind of knowns and my unknowns, what I'm trying to go for. So usually when you set these things up, there's something you don't care about. It's either not given in the problem. Well, first of all, it's both not given and it's not what you're asked for. So it's the variable you don't care about. So if nobody asks you about the change in position, then you can use equation 2.52. If nobody asks you about what the final velocity is, then you can use equation 2.53, that second one. And if nobody asks you how much time passed, then you can use equation 2.54. So we're going to do another equation. For one-dimensional motion with constant acceleration, it turns out, and this is something I didn't really explain, that the average velocity is half of the initial velocity plus the final velocity. So I can write that out for you. V average is equal to V0 plus V divided by 2. And this thing right here is true only when the acceleration is constant. So that's like a little addendum to that. And then also, by definition, you know that V average is equal to x minus x0 divided by t, the time. So you got these two equations, and I guess you can combine them. You can say V average equals V average. So that trick when acceleration is constant is V0 plus V divided by 2, and the definition of acceleration gives you x minus x0 divided by t. And you can solve that out, and you got the x minus x0 equals v0 plus v divided by 2 all times t. So that becomes the fourth equation in this list. Sometimes they're called the four kinematics equations. This last one in your textbook is sort of a combination of equation 2.50 and 2.51. So I've kind of combined it. But these are the ones that if I were you, I'd put on my 8 sheet. Newton's first law, which is going to be more of a chapter 4 concept, but I want to introduce it right now because it'd be super helpful for practicals. It says that for an observer in an inertial reference frame, which means just one that's not accelerating, if the net force on an object is 0, then the object either stays at rest or moves at a constant velocity. And I guess constant velocity in a straight line. There's a lot of different ways of stating it, but this is one way. Basically, if you've got a frictionless cart on a straight path and you start it with some initial velocity, its inertia will carry it forever. Okay, next thing I want to do is go through a little bit of relative motion. So if we know that there's some object, A, okay, and it's moving, in some reference frame, maybe this is like an eyeball or something like that, 1, then it's got some velocity VA in reference frame 1. This mic just keeps cutting out on me. It sometimes works and then it goes in and out. So I don't know if you have a spare. Thank you. So this is velocity. I put A and then 1 of object A relative to reference frame 1. We can transform it to a different reference frame, which is if you've got another observer, this is another eyeball, which is moving along at some V21. This is the velocity of reference frame 2, so this is 2, relative to 1. So a different observer. Then we have that VA in the 2 is equal to VA in reference 1 minus V21. So this is sort of a way of transforming velocities. Okay, so I do have a joke, but it's, again, not a very good one. It's why the chicken crossed the road. Maybe you may have heard of this one. It's an old one, but so if it was Aristotle from 330 BC, you might say, because it is the nature of chickens to cross roads. Okay. But if it was Newton in 1687, you'd say because there's no external net force on the chicken, causing its velocity to change as its velocity is already directed across the road. And then if it was Einstein, 1905, he would say, well, wait, is the chicken crossing the road or is the road just passing underneath the chicken? Okay, so this is a relative velocity, so what we're going to do is now, I have a remote-controlled car with a camera hooked up to it. Let's see if I can you guys see it? Alrighty. I should not be driving this thing, nor should I be throwing microphones to balconies, but there it is. There's your little car. I'm getting used to it. Is there a... Yeah, there we go. So this shows a little camera showing the car's perspective on the world. So as it drives along, whoop, no! It's exactly, sorry man. I wanted to line it up so that the audience is in the background. Yeah. I didn't kill it. There you guys are in the background. So now I can make this whole class travel that direction. All I do is, the car is stationary according to that little camera. Okay, so I cannot go backwards, right? But I'm gonna hurt somebody. Beep, beep, beep. Whoa. Okay, so there you go. So this is this idea that velocity is relative, and you may even think actually that you're sitting still right now, right? Because if we're calm, we're sitting still. But right now, I would argue that in another reference frame, you are moving at 30 kilometers per second as the Earth orbits the Sun, which is actually pretty fast. The whole Earth is moving 30 kilometers, 30 kilometers, 30 kilometers, 30 kilometers. If you think about that, we're really going fast right now. I'm not sure which way we're going, but one of these directions as the Earth goes, and that's relative to the Sun. Don't forget also that the Sun is orbiting the center of the galaxy at 220 kilometers per second, I think. And so that's also a velocity you should take into account. So, but even then, maybe the Milky Way galaxy has its own space velocity through, I don't know what the standard of rest is, but in Einstein's theory, oh, there we go. Let's go back to the laptop. Thank you so much, John. That's a new demo, so. Never been done before. Special relativity says that there is no special reference frame that you could say is at rest. All inertial frames that are not accelerating are equivalent, and there is no experiment that you could do to determine whether you are at rest or whether you are actually moving. It's just velocities are relative. Okay, so there's these 4 equations of constant acceleration, and I'm going to go through some examples of doing problems with all 4 of them. There they are. We introduced them last time. They are derived quite carefully in Chapter 2, so I did not derive them in front of you. So I think it's a good reading assignment if you're curious about it, to go through where they come from. Yeah, so we're going to go through ones that use these equations. So and I'm also going to try to explain to you some of my reasoning of how I do problems. So step 1 is always draw a diagram. You can do these any steps that you want, but my thing is that an Olympic crest sprinter, so I draw a person who's kind of running, starts a race with an acceleration of 4.5 meters per second. So the other thing I do is I list knowns and unknowns. And I might even do that on the diagram. The reason I have these particular steps, partly, if you want me to tell you the truth, is to manage my anxiety on tests. I have test anxiety, so when I sit down to do a physics test or something, when I was a student anyways, my heart would be racing, I'd be feeling really filled with basically adrenaline, and that's not a good situation to be in. It's hard to think when you're anxious. So doing these steps in this order was something I did as a ritual to calm myself down. So even if it wasn't super helpful, it is helpful actually to have this for me anyways. So for example, A is equal to 4.5 meters per second. And then once I write it down, I was wondering about the sign. So let's define, while I'm doing this here, your x-axis. So put plus x to the right here. Yeah, I think I'm just going to define x equals 0 to be x0 to be 0 right there. And then this is plus, because he's going to the right. He goes over here, and then he's running faster, I think, right? And then I guess maybe it actually doesn't say what v0 is, but I think it's starts. So what I'm going to do is assume, even though it doesn't really say this, that v0 equals 0. That it starts a race, so maybe I think this is going to be important. And then it says, what is her speed 2.4 seconds later? So t is equal to 2.40 seconds, and v is equal to question mark. I need the final velocity, or the speed actually, which is going to be the absolute value of the final velocity, but that's okay. So then the step 3 is the Dora the Explorer used to say, let's stop and think. So it's to think about how to solve this problem. So you kind of have to look at your diagram and think about this chapter that you're in. This looks like a chapter 2 problem to me. It's kinematics. There's no forces. You're just given an acceleration. So it's also in 1D. There's no turning or anything like that, or circular motion. And also, I like to think about what don't we care about. If you look back at those equations, they're here, they don't contain certain things. So there's usually something that you're not asked about and you're not given. And I think in this case, it looks like it's x. So let's pick the equation that doesn't have x, position. And that is the first one, equation 2.52 from your book. V is equal to v0 plus a times t. You're solving for v, which is already solved for, so that's easy. So this is, by the way, this is step 4, which is I call it do the math. You're going to have to do that, but the equation's sitting there, so it's not too bad in this case. So then, since it's there, let's just plug in the numbers. I got 0 plus acceleration is 4.5 times the time, which is 2.4. And we'll get v equals, on my calculator, 10.8. Don't forget the meters per second. Okay? And then, I guess step 5 is what I call, I don't know if this is a good word for it, sanity check. I would just say, is this result, does it make sense? So can sprinters run that fast, actually? Try to compare it to your experience of the real world. And I would say that 11, maybe you could convert it to kilometers per hour, for example. I think there's 3,600 seconds in 1 hour, and there's 1 kilometer equals 1,000 meters. So if I was going to convert units, seconds would cancel seconds, meters cancels meters, and if you times by 3,600, divide by 1,000, you get like 40 kilometers per hour. All right. At the end of a race, a runner decelerates from a velocity of 9 meters per second at a rate of... So while I'm reading it, I'd like to, again, draw a diagram. So there's a runner, which is starting off pretty fast, I guess, from a velocity. So I think the V0 is the 9.0 meters per second. I'm going to, again, define plus x to be here. So this is like drawing a coordinate system on my diagram. It's only one dimension, but I could put y is up and x is to the right here. This means like slowing down. So what that means is that acceleration is opposite sign of velocity. If the velocity was plus 9.00 meters per second, I would say the acceleration, it says that it's 2.00 meters per second squared, but since it's slowing down, I have to make that the opposite sign of whatever I made the velocity. So I'm going to put a negative there. Otherwise, probably my math is going to be wrong at some point. And then it says, how far does she travel in the next 4 seconds? You're here. This is some distance x. So x is question mark. That's what we need this. Need x. And then this is at time is equal to 4.00 seconds. And it doesn't really say that she's stopped. I will just say that the person may still be moving, I guess, forward at the end. I'm a little curious about that, but I'm not asked about it. But basically, we don't care about V. So what we'd use is, let's pick the equation that does not contain the final velocity. So I think it's equation 2.53. It's x is equal to x0. Oh, and I'll say that this is x0 equals 0. Plus v0t plus 1/2 a times t squared. And again, we're solving for x, so it's already solved for x, so we can just start plugging in. 9 times 4 plus 1/2 negative 2 times 4 squared. And so I've got 9 times 4 is 36. 4 squared is 16, and times by 2 and divide by 2, I get minus 16. So I get x equals 20 meters. So that's the answer. My little last step, maybe I'll call it sanity check, does this make any sense, is let's use equation, because I'm kind of curious about the final speed to find the final velocity. V is equal to V0 plus A times T. So it's going to be the plus 9 plus negative 2 times 4. I kind of really want that to be positive because I can't imagine, first of all, sprinters having constant deceleration anyways, but if they actually slow down, stop, and turn around and going back the other way at constant acceleration, that's just totally absurd, right? So, but luckily it's 9 minus 8 equals plus 1 meters per second. So I would just say, good. Still going forward. If it was negative, I would suspect that the whole question was kind of silly. Oh, and the other question is, what if you do it a completely different way? So there is actually multiple ways of solving these problems, and that's perfectly fine. Like you could have used another equation and then combined it with one of the other ones. Whatever way works for you, as long as your reasoning makes sense. Okay, example 3. You're traveling at an initial velocity of 30 meters per second. I would say in a car. because there's something about brakes. I think this was something we did before, isn't it? Let's define plus x to be to the right, x0 equals 0. And then we would say that this v initial is now plus 30 meters per second. At position x equals 0, you apply the brakes, which gives you a constant acceleration of a is equal to minus 10 meters per second squared. And then it says, how far do you travel before stopping? So I would put here that stopping means that v is equal to 0, the final velocity is 0, and then this distance x is question mark, and you need this. And I would just say, what don't we care about if we're trying to think about this, and we'd pick an equation to use. It seems like time is not asked here. And so for that one, so let's use the one that doesn't have a t in it. It's 2.54. Which was v squared equals v initial squared plus 2 times a times x minus x0. But this, don't forget x0, we defined that to be 0. So in this case, you are asked for x, but this equation doesn't give x, so what you have to do is solve for x. This is part of doing the math. This is like where are we here? This was 1 and 2. This was 3 is thinking, now we're on the step 4, do the math step. So solving for x would be, let's rearrange this. So v squared is v0 squared plus 2ax. Let's subtract v0 squared from both sides. Equals 2ax. And now let's divide both sides by 2a. If you go 2a and 2a, you get that these cancel, and you get x is equal to v squared minus v0 squared all over 2 times a. So now we've got to plug all the numbers in. V is 0 squared minus v0 is 30 squared divided by 2 times the acceleration is minus 10. And they're all in SI units, so I'm not going to write down the units in the calculation, but I get that x is equal to 900 divided by, negative 900 divided by negative 20. I got 45 meters. And then my step 5 is this is the same as Kamala got last class. I don't know if you guys know what I'm talking about, but last class, Kamala Harris was thinking about sort of that the average velocity here is about 15 meters per second, because it starts at 30, goes to 0, the average is 15. It also seems like if you're starting at 30 meters per second and you lose 10 meters per second, it's going to take you 3 seconds to go that far. 3 seconds multiplied times 15 average velocity, 3 times 15 equals 45. So that's kind of it all seems to work out. Yeah, this seems pretty good. A motorcycle accelerates from rest to 26.8 meters per second in 3.9. So what I'm going to do is draw it. Draw a diagram, that's my first step. It doesn't have to be beautiful, but V0 is equal to 0. I'm going to have x going in that direction. I'm going to define x0 equals 0. And it says V is equal to 26.8 meters per second. That's like the final. And T is equal to 3.90 seconds. So I've listed my knowns and unknowns. The question is, how far does it travel? So X is equal to question mark. Need X. So if I was trying to think about what we don't care about, what don't we care about maybe? I mean, we could find it, but I think it's actually acceleration. It says, it doesn't say what A is, but it says assuming constant acceleration. But we know it's constant. Now I think, as I mentioned before, that may not be a very realistic assumption, but if we do assume that it's constant, then we can use equation, I call it 2.50 plus 2.51. They display it as two equations in the book, but I think it's better to just write it down like this. V initial plus V final divided by 2 multiplied times the time. It's the average, the change in position is the average velocity times the time. And then we can just solve that out. So it's equal to 0 plus 0 plus 26.8 meters per second divided by 2, all times 3.9. So I got, this is 13.4 times 3.9. I got 52.26 meters. I guess we could round it to 3 significant figures if we want. 52.3 meters. And then, I don't know if you want to do like a sanity check or whatever, that does make sense. Check. Reality check. 4 seconds, 50 meters. It's pretty fast, but it is a motorcycle. It's not always obvious how to do these checks, but sometimes just kind of look at it and see if it seems all right. If we'd gotten 5 millimeters or something, maybe we would wonder if we were doing it right. So I want to actually do a thought experiment. So if you have a brick and it has a mass of 2 kilograms, it'll fall at a certain rate. What if you had a double-sized brick that has a mass of 4 kilograms? Should it fall faster? And this is one of those examples, so I think it's good to use your intuition when you think about physics, and we all kind of, I think we're scientists when we were young children, and we learned physics on the playground by actually trying things and repeating our experiments. And if you think about, for example, a hammer and a feather, which will fall faster, well, your intuition tells you the hammer is going to fall faster than a feather. And that's correct, obviously. So there's this idea that somehow more massive objects fall faster. So think about this thought experiment. What if I took 2 bricks and made a little gap between them and attached them to each other with a tiny, thread that's extremely strong and can't snap? Or maybe if there wasn't such a big gap, they were really far apart from each other, 2 just bricks, and I dropped those. So it's 1 4-kilogram object. Do you think that should fall faster than a brick all by itself without the wire? It sort of seems to me like this is just 1 brick, but again, and the wire shouldn't pull it down any faster, I think. So there's this idea that free fall under the influence of gravity only with no air resistance has this rate of 9.8 meters per second every second. And the exact value of this free fall acceleration depends where you are on the Earth. It's a little less if you go up onto a mountain because you're farther from the center of the Earth. It's a little higher at sea level. For this course, we're just going to use 9.8. And it's an acceleration, so after 1 second, if you release something from rest, after 1 second, it's going 9.8 meters per second. After 2 seconds, it's going 19.6 meters per second. After 3 seconds, 29.4. It gains this about 10 meters per second every second. And so if you look at the distance between where something is at subsequent points, it keeps increasing, like that distance keeps increasing as you go faster and faster as you fall. And this is, of course, why it's much worse to fall from the top of a building than it is to fall off a few steps or something, is that as you're falling, you're picking up speed. So even though the force of gravity of the Earth on the basketball is more than the tennis ball, they fall downward at the same rate. This was first popularly talked about by Galileo, and apparently there was even a breakfast with the Pope one day where Galileo asked the Pope to predict which would fall faster, a grape or a grapefruit. And the Pope predicted that the grapefruit would fall much faster since it's heavier. And then Galileo showed the whole thing. Galileo ended up under house arrest for the rest of his life. And so now we have tenure so that people can say controversial, crazy things that even defy the Pope, and we don't go to jail. We don't get fired, so that's a good thing. It's a bit, and then there's this pre-class survey. I wanted to just go through this. If I drop an object a distance of 14 meters above the ground, and it falls with negligible air resistance, how long will it take before it hits the ground? So you can use those same equations. So it doesn't really say, but I'm going to assume that V0 equals 0, it's dropped from rest. This is often the case with these things, dropped from rest. And what that means, it's the same thing I just did with those basketballs. I was very careful not to like throw them up or down, but just to release them. And then it falls, how long will it take? So need t. Y is equal to 14 meters. Y0 equals 0. And it seems like we don't care about the final velocity. And what this means, it's a little strange as well, is it would be during this free fall, the velocity that the object has just before it hits the ground. So you could calculate that, but in this case, we don't care. So we're going to use equation 22.53, the one that doesn't have final velocity, which is y is equal to y0. Instead of x's, I'm going to put y's just for fun, plus v0 t plus 1/2 a t squared. We're going to say that a is equal to 9.8 meters per second squared. So this is 0, this is 0. So you just get y is equal to 1/2 at squared. We can times both sides by 2. 2y equals at squared. Divide both sides by a, you get 2y over a is t squared. So t is equal to the square root of 2 times y divided by a. Square root of 2 times 14 meters divided by 9.8 meters per second squared. So if I've kept everything in meters and seconds and kilograms, then hopefully this will all cancel out. I just typed those numbers in my calculator and I got 1.69 seconds, which is closest to, oh yeah, so this is good. Whoever did this in the survey did a good job there. Thank you. After the object hits the ground, will it bounce back? That's a great question. And so it might, right? But the idea with physics is that often what we do is we try to simplify things and we model things, the things we can understand. So for example, if I take a ball and throw it or something, then there's the throwing motion, which you'd think would be important, and it certainly is. We just ignore all of that because it involves a bunch of forces from a human hand on the ball. And then, just after I release it, well, now it becomes something I can analyze using these equations. So the initial velocity, usually, that we use for when we're solving problems is just after it leaves my hand. We forget about all the motion during the hand. Then it flies along, obeying very simple laws of physics. And then, just before it hits the ground, we still are using the easy equations, but then it hits the ground, and again, there's an external force that's not gravity, and so it starts messing it up. Actual motion is complicated, but just after it leaves the hand to just before it hits the ground, that's something that we use these equations for. Are these equations basically the kinematic, but in the vertical direction? That's exactly correct. Somebody noticed that. Just replace the x with a y, and replace the a with, like, negative g, I guess. Can a human live on a planet that doesn't have g as 9.81 meters per second squared? Well, I hope so. I mean, humans have been living in space where gravity is like 0 effectively, right? So Mars has 3.17 meters per second squared as its gravitational acceleration, so we would hope humans can live there. Yeah, this was another thing I wanted to do. If we have two pieces of paper, these have the same mass, so we can drop them. But what I could do is crumple one up. So now which is more massive? Well, they're not. They're the same mass, I think, still, right? But if I drop them, which do you think is going to hit the floor first? 1, 2, 3. Boom. It didn't even hit the floor at all, it hit the table. But basically, something's going on here with the non-crumpled paper, and it's called air resistance. So that's sort of the point here. Why does the crumpled up piece of paper fall faster than the non-crumpled up? The non-crumpled paper has a much bigger surface area, and it's kind of like a sail as it falls, right? If there's wind, which is going to sort of support it. So, as it's falling, there is an upward, in addition to gravity pulling it down, there's an upward force of air resistance. It's like if it's maybe falling through water or some kind of fluid. Air is a fluid, right? So you have to push your way through it, through the fluid of air. So the non-crumpled piece of paper has a smaller surface area, and so that air resistance is less on it, so it falls closer to this 9.8 meters per second squared, which it would if there was no air at all. Okay. So, and that's true of many light objects such as feathers. And this is the real reason why a feather falls faster than, sorry, why a hammer falls faster than a feather, is because the air resistance on a feather compared to its weight is pretty big, whereas the air resistance on a hammer compared to its weight is very small. It's a comparison there. And if you were to somehow pop out all the air in the room and drop the hammer and the feather, what I'm telling you is that they would both fall at 9.8. Okay, should we do an example? Some people in a hotel are dropping water balloons from their open window onto the ground below. The balloons take 15 seconds to pass your window. So they're above you some distance, and you would like to, when you're phoning down to the front desk, to give them an estimate of how far above you these guests are. And you time it just passing by your window to be 1.6 seconds, sorry, 0.15 seconds. It's pretty good measurement there. So the way I would do it is, here is your window. It looks like this. It's got a height of 1.6 meters from here to here. And these water balloons come with some initial speed, maybe V1 or something, and they leave with some speed V2, which is greater. And the idea is that if I set T1 as 0 seconds here, at T2, you're going to be 0.15 seconds. This is the time to travel the height of your window. So what we need to do is find how far above your window that they were released from rest. So that's another assumption, I guess, is that whoever was dropping these things was releasing it from rest. The balloon, which falls without air resistance, I guess, because it's filled with water, released from rest. Try to keep handwriting a bit better. So we will assume that the initial drop was from rest. And then we're going to divide. What I'll do is I'll divide the motion into two segments. The before it gets to the window, and then after, as it travels your window. So segment 1 is before, this is what we kind of care about, right? The balloon gets to the top of the window. So V initial here is 0. And then what happens is that V1 is the final speed here, final velocity. And what we need is like Y1 is the distance traveled. That's what what we're asked for in this question, and what we're going to call up to security about. And what we don't care about is the time to do this. So we were given some time, but that's the time of segment 2. And then the next thing is segment 2 is V1 is this initial, which is the final time of segment 1. So I'm going to take the final velocity of that first segment and make that the initial velocity of when it's going past my window. And I know that T2 is equal to 0.15 seconds, and Y2 is equal to 1.6 meters. And we don't care about the final speed in this case, how fast it's going when it reaches the bottom of my window, V2. So, we can just try to solve that. So segment 1, we can use equation, since we don't care about the time, we can use equation 2.54. And we'll solve, it looks like this. 2a will solve for V1. 2 times a times y1 minus y0 is equal to v1 squared minus v0 squared. So y0 is 0, v0 is 0 because it's dropped from rest. The acceleration is 9.8 meters per second squared. So you get 2 times g times y1, which is what you're looking for, is equal to v1 squared. Now I don't know what v1 is, but I'm going to find that out from segment 2. So I'll just leave it in equation form. v1 is 2gy1. And then for segment 2, Since I don't care about v2, the final speed, I'll use equation 2.53, one that doesn't have, and I'll solve for v1. And then I'll combine these two equations, and I should be able to finish this problem. y2 is v1 times t2 plus 1/2 times this acceleration times t2 squared. So v1 is equal to y2 minus 1/2 a t2 squared divided by t2. And then, so we've got this equation, which is shifted over to the left. We've got this equation, and we've got this equation, both for v1. So I'm just going to set v1 as v1, depending on what we got it from. Square root of 2 times g times y1 is equal to y2 minus 1/2 at squared divided by, that's t2, by the way, divided by t2. So we can square both sides. We'll get 2g y1 is equal to, maybe we should change this to g. The acceleration is g. So this y2 minus 1/2 g t2 squared divided by t2 all squared. Y1 is equal to 1 over 2 times g times all this stuff squared. And I just plug in all these numbers and we'll be done. Divided by t2. Okay. So y1 is equal to 1 over 2 times 9.8 times 1.6 minus 1/2 times 9.8, that's a 6, times 0.15. 0.15 squared. And then square the whole thing, divided by 0.15. And if you plug in all those numbers, I think you get 5.03 meters. So basically, security should look 5 meters above the top of your window. A couple stories up. So this is an example of dividing your motion into segments. And the idea being that the final position and velocity of your first segment becomes the initial position and velocity of your second segment. It's a pretty powerful way of solving one of these more complicated problems. So I do want to talk about graphical motion, graphical method for finding displacement. So the slope of a position versus time graph gives velocity, and the area under a velocity versus time graph gives displacement. So this comes up sometimes. So here's a velocity versus time graph of an object that's at the origin at t equals 0 seconds. So how far does it get? And so, and basically, let's remove some of these. I'm going to take the area under that curve, and that's going to tell me how far it went. So thanks for your patience. I would say we can, first of all, split it into two things, a square and a rectangle. So A1 and A2. A1 is the square, or it's a rectangle. So, and what's interesting is that it looks square-like, but actually the units of the height are different than the units of the width. One is in meters per second, and one is in seconds. But length times width, so it's okay, we can do that. And A2 is a triangle, and the area of a triangle is 1/2 base times height. So at t equals 0, x0 equals 0, and Vx versus t graph is given. So the area under the Vx versus t graph gives displacement. That's the concept here. It's the last concept of chapter 2, actually. So delta x is equal to x minus x0. So delta x is equal to the area under the shape down to that t-axis, a1 plus a2. So it's going to be length times width plus 1/2 base times height. So the length here is 2 seconds for this triangle, times the height is 4 meters per second, for the rectangle, plus 1/2. This also has 2 seconds on the bottom, is the base, 2 seconds, times also the same height, 4 meters per second. So it looks like this, 8 plus 4. So delta x is equal to 12 meters. So the final position is 12 meters. And in calculus, we call it an integral, but we're just using, in this class, area under the curve.